So first, I'll give a little bit of background on physical electronics. We are a surface analysis instrumentation manufacturer, and we specialize in 3 different techniques: XPS, or X-ray photoelectron spectroscopy, Auger, electron spectroscopy, or AES, as well as TOF-SIMS, time-of-flight secondary ion mass spectrometry. As you can see here on the screen, we have a few different products available for these. These are complete systems. In the XPS line, we have a Quantez, which is actually a XPS and HAXPES system, so we can do both soft and hard X-ray analysis. We also have a Quantera 2, which is a more high throughput type of XPS system. And then our VersaProbe 4, which we have just released, which is our latest edition of our multi-technique scanning XPS microprobe. So we have a lot of options and analytical capabilities on that I'll touch on a little bit later on. For the Auger, we have a multi-technique system, our 710. And for the TOF-SIMS, we have a new product, our NanoTOF 3, which is our latest generation with our tandem MS capabilities. PHI is a subsidiary of ULVAC-PHI, which is based in Chigasaki, Japan. The physical electronics office where I am now is in Chanhassen, Minnesota, just outside of Minneapolis. In our site in Minneapolis, we do sales and service for essentially most of the world except for Asia. We have here in Minnesota a demonstration lab as well as a contract lab and some R&D as well. So the basic outline for today's talk, for those of you who are not familiar with some of these techniques, I'm going to go over a brief overview of each of them. And then we'll talk a little bit about some of the trends in battery materials and some of the questions that are in the field and that are still waiting to be answered. Then we'll talk a little bit about how we practically analyze these types of materials using some of the techniques here. We'll show some examples of looking at anode passivation layers, the SEI development, as well as some other things like dendrites and some of the tips and tricks that you may need to think about when you're analyzing these types of materials. And then I'll talk a little bit about some of the advanced characterization options we have available with our different systems. So to start with, I'm going to start with XPS, which is X-ray photoelectron spectroscopy, also known as ESCA, or electron spectroscopy for chemical analysis. And the general outline of this technique is it uses the photoelectric effect in that a X-ray photon, typically a soft X-ray, about 1400 eV photon energy, will strike the surface, and that will be absorbed into the sample and emit a photoelectron from a core energy level. And that photoelectron will have a kinetic energy as it passes through the sample. It will lose some of that energy through collisions and then be ejected into the vacuum. And we can collect that photoelectron, measure its kinetic energy, and then based on the photon energy, back calculate the binding energy of the orbital where it was emitted. And so from that, we can kind of get a fingerprint of the element and composition within our sample. And so a short example here, this is what a typical survey spectrum looks like for XPS. You see that you have strong peaks that would be representative kind of fingerprints for different elements at specific binding energies. You'll notice also that some elements will have multiple peaks, and so you can use those again for fingerprinting. And one of the real advantages of XPS is the ability to not only get elemental information, but to get chemical state information, kind of short order chemical state bonding information. As shown here on the right with this spectrum for PET, a polymer, we are looking at the carbon 1s spectrum narrow scan or high resolution scan. And we see we have multiple peaks out of the original somewhat single peak that we saw in the survey. And so each of these are representative of a different chemical state, whereas carbon may be bonded to carbon here, bonded to oxygen, different bond to oxygen. So depending on the electronegativities of those bonds, you will see some different shifting of the peak, and we can use that to quantitatively investigate the type of material. And so in this case, we have a very large carbon-carbon peak, which would be similar to what we see here in this ring structure, and then some carbon-oxygen species, which match up with the species shown here kind of in blue and in green. So this is where the power of XPS lies into to see chemical states and then chemical state changes as we process materials. The next technique is Auger electron spectroscopy, also called AES or SAM for scanning Auger microscopy. And it has a kind of a similar method to it. Rather than having a photon hit the sample, we will be using an electron beam. So the incident beam will interact with the sample, knock out a core level electron. And then what will happen is a electron from a higher energy level will fall in to fill that vacancy. And in doing so, it will release a given amount of energy related to the difference between these two energy levels, which could be transferred to a third electron. And if that is sufficient to overcome the binding energy of that orbital, then this could be ejected. And so this is the Auger electron. So it is a 3-electron process for Auger spectroscopy. And this is a typical spectrum you would see for Auger on the right. So normally you have a very large background. And because of that, we typically differentiate the spectrum and use, again, fingerprinting of different peak positions to identify what elements are in our sample. And the power of Auger is in the high spatial resolution. Since we're using an electron beam, we can get down to single nanometer type of beam sizes. So that gives us very good spatial resolution on our samples. As you can see here on this material, this is a nickel silicon sample with a lot of texture that we can see in an SEM image. And if we do Auger mapping, we can see some different features of, in this case, red is carbon, green is silicon, and blue is nickel in the 100 nanometer type of range and below. So again, getting very good spatial resolution with Auger. And our last technique that we'll be talking about today is time of flight secondary ion mass spectrometry. In this case, we are using a primary ion beam, typically something like bismuth, to strike the sample and generate secondary ions. Those are directed toward a mass spectrometer where the time of flight separates the different species based on their mass to charge ratio. One of the nice features about this particular instrument, the NanoTOF-3, is that we have a tandem MS capability. So if we have a mass to charge value that we're trying to understand better, we can pick it off and actually send it through a second collision cell so it can be fragmented again to give us better understanding and a better unambiguous characterization of that particular material. And you see here in the image, what we will get is a mass spectrum, and we could then map out different species to show where they are. And with TOF-SIMS, we're getting a little more molecular information. So from, if I go to the next slide, just to compare these different examples, with Auger, we have a very good spatial resolution, but we're getting more elemental type information. With XPS, we have a slightly larger beam, but we're also getting more chemical state information. And with TOF-SIMS, we're going up a little bit further and getting more molecular information. So it's very good if you have organic type of materials, whereas Auger and XPS would show you that you have carbon, oxygen, nitrogen, for example, but TOF-SIMS could really differentiate between similar organic type of compounds. Now, all three of these techniques have very good depth resolution, and that's where these shine in these type of applications. The surface information depth is on the order of just a few nanometers up to maybe about 10 nanometers, depending on the technique. As you can see here, TOF-SIMS has a sampling depth of just a few nanometers, whereas XPS and Auger are on the order of about 5 to 10 nanometers. And so this is very good for investigating surfaces and looking at things, how reactions are progressing or defects on your surface, or maybe functionalization of a surface. These are all very good techniques for characterizing those type of applications. And a variety of industries are using surface analysis for these needs. And so if we apply this to energy research and batteries, there's a lot of emphasis right now on moving away from fossil fuels, looking toward energy storage, battery materials with high capacities, fast charge rates, and that are safe. We have lithium-ion batteries with liquid electrolytes have suffered fires and failures and things. So there's a need to improve on those methods and technologies for safer batteries. We're looking for batteries for electric cars, for mobile electronics, and a variety of other needs. And so we're, of course, looking for technologies, materials that are cost-effective, safe, and high performance. And these are all complex, multi-layered, multi-phase type materials going through a lot of different process steps. And so we can use these surface analysis techniques to really understand them kind of at each step along the way. And so if we look at a general schematic of a battery, we have a few different components to it. There is a cathode, an anode, and that is what will be the charge carrier will be moving back and forth between those two different electrodes. And then in doing so, we will be also moving electrons outside of the circuit. And so as in this case, lithium moves from the cathode to the anode, it will be passing through an electrolyte material. There's also some organics in there as well. And so these anodes and cathodes have been traditional anodes might be something like graphite, where the lithium can move in between the different layers of the graphite. Cathodes might be something like a lithium cobalt oxide. But we're seeing things like cobalt is a somewhat rare material, and we'd like to move away from cobalt materials. So there's a variety of other oxide materials and others that are being used instead of that. The electrolytes, the salts, the different charge carriers, there's a lot of different emphasis for improving capacities and capabilities. And so again, we have organics, inorganics, things changing with time. And so a lot of the questions we might ask are, just in general, what are the quality and purity of my raw materials? What am I starting with? And then after I put it through some sort of performance test, voltage cycling, thermal cycling, what has changed? What chemistry has changed? What mechanical properties have changed? And so those are the kind of questions that we'd be wanting to ask. And for a lithium-ion battery, there are a lot of sort of things that can happen. We have chemistry happening as the lithium moves in and out of these electrodes. There are reactions happening at the surfaces where it's breaking down the electrolyte material. The lithium, as it moves in, can cause swelling of the electrodes. And so there's mechanical stresses happening in there. And as those happen, we might start getting electrochemical migration of, say, lithium dendrites that can then move across and short circuit the battery. And so we really just need to understand kind of at the very surface level what reactions are happening. And so with these degradation mechanisms, we can see reduced capacities and possible safety concerns. So if we want to perform successful battery analysis using these type of vacuum techniques, Auger, XPS, TOF-SIMS, there are a few criteria that we would try to meet. So the material does need to be vacuum compatible. So for some of the newer solid electrolytes or ionic liquids, that's not so much a problem. If you are using liquid electrolytes, you would likely need to wash that from the circuit after you've done your testing before you put it in the instrument. We'd like to have some kind of heating capability built into the instrument because some of these, the operational conditions are not always just at room temperature. So we'd like to simulate that and watch this happening somewhat in situ in the system. Lithium is extremely reactive. And so if we don't handle the samples in very controlled ways, we will get side reactions that we want to avoid. We would also like to have electrochemical cells so we can charge and discharge these batteries in the system as well, again, to simulate sort of actual conditions. Typically, a lot of the cycling is done outside of the analysis chamber, and then the sample is maybe taken apart if it's a coin cell, and then moved in sort of piece by piece into the system. And so you may or may not be changing or getting different results if you had something somewhat in the system already. And so sample handling can be done a few ways. In production facilities for lithium-ion batteries, typically these are dry rooms where the humidity is controlled to a very low level. We also, if you're working more at an R&D level, you might be working in a glove box, which is typically going to be an argon glove box, again, with low humidity and oxygen. So for our systems, example, the VersaProbe, which is our multi-technique XPS, we can hook this directly up to a glove box. And so you can process your material in the glove box on a transfer arm and then move it into the system. We also do have transfer vessels, which can be used to move outside the system, but within either a vacuum or a pressurized atmosphere of, say, argon, to minimize any kind of air exposure that might degrade your material. And this just shows the with and without the transfer vessel, what you may expect to see. If you transferred a lithium foil just in air, it will quickly form a passivation layer of hydroxides and carbonates, and you wouldn't really see any sign of a lithium metal, for example. In this, with the transfer vessel, this sample was sputter cleaned and then put in a transfer vessel from a glove box and moved in and out. And you can maintain some of the lithium, but you are seeing carbonates and hydroxides form fairly quickly, even when you do that. So getting into kind of our first example, we want to look at how we can use XPS analysis to understand the passivation layer on, say, a lithium anode foil. Lithium foils are under investigation as replacements for carbon-based anodes, just because they have high volumetric and gravimetric energy density compared to carbon-based anodes. But there are some problems, especially with this very high reactivity and being able to control that as you then combine this with other electrolyte materials and so on. And so the general idea is that if you have a bulk lithium, you probably have a lithium 2 oxide on top, and then a lithium carbonate lithium hydroxide. And with XPS, we can look at those different binding states of the lithium material to understand the relative intensity of those states. As shown on the left, we're looking at an oxygen 1s peak for a lithium passivated foil that has basically not been sputtered, so it's just somewhat as received. And we see essentially carbonate and hydroxide species in both the oxygen and lithium. But we do a little bit of sputtering, and then we see that there are some differences in the states, and we actually get more of a lithium 2 oxide state showing up. And then with further cleaning, we eventually get more to a pure oxide with a little bit of the oxygen shows an oxide state. With the lithium, we also do see the eventual emergence of a peak at low energy, which would constitute kind of a metal. But again, this is typically short-lived, because even the residual gas in the chamber can cause it to reoxidize pretty quickly. And so what we're looking at maybe are different coatings or surface treatments that we can put on the lithium foil to passivate this in a controlled way. Another area of interest is the SEI layer. So the solid electrolyte interphase layer is what is formed when you put a somewhat a pristine anode material combined with your electrolyte, your other materials, salts and whatnot that go together. And so as you discharge and charge the cycle a few times, you will start to get some decomposition of those products and some reaction products forming on that surface. And in order to maintain good ion conductivity, that is an area that we would like to control. So there are certain phases, mechanical phases or grain sizes that you would like to achieve, certain reaction products that have good ionic conductivity. And so what we are showing here that we can use XPS for is to look at essentially a pristine material. This is a lithium titanate material. And this, with pristine, we essentially are seeing carbon fluorine type bonding. This would be our fluorine bond, fluorine 1s region. And in our oxygen 1s, we see the oxygen mostly from the kind of the titanate. After we cycle a couple times, 100 times, we do see emergence of a lithium fluoride type species, which is one of the decomposition products. And depending on the temperature that was used for these cycling studies, we can see different products emerging. And so we can then look at that as a function of the performance of the battery to understand, okay, which chemical component is maybe restricting my performance, and then optimize your battery that way. With a similar technique with Auger analysis, again, using our high spatial resolution, we can look at these SEI type layers. And what we're seeing here is a lithium manganate type material with carbon black. And after cycling, we can see some different features around the borders of the manganate material. So using the high spatial resolution, the scale bar here is about 2 microns. High spatial resolution, we can map out where those features are after we cycle. We can also use TOF-SIMS to look at the SEI layer as a function of cycle times and things like that. In this case, we have a lithium titanate and a nickel, I believe it's a nickel manganese cobalt material. And so we see different species at the top surface after the first cycle. And then as we continue the cycling, what we find is that there are actually some components from the manganese, the opposite electrode, have started to migrate over to the other side of the system. So there appears to be some breakdown in the system where we're seeing different migrating species back and forth across the electrolyte. But we can also map out things like the lithium fluoride, which is the green, and how that develops with multiple cycles. Another area of concern is dendrite formation. These can sort of evolve from defects on our electrode material, and then can, as you see here, kind of sprawl out and eventually maybe cause short circuiting or other deleterious effects. And so with XPS, what we're looking at is the spectrum from 2 different regions, and this is an SXI image that was collected on a VersaProbe. So an SXI is a scanning X-ray image. One of the advantages of the PHI instruments is that we scan our X-ray beam, and so we can collect an image from the sample by scanning the X-ray beam and then collecting secondary electron images, similar to kind of like an SEM. And what we see here are areas of bright and dark, and that's related to a secondary electron contrast between different regions. And we can choose points on and off of that to see what the chemical differences are. And in this case, what we do find is that there is more of a lithium fluoride type development in on the dendrite area. And this is something that because of the surface sensitivity of XPS, it may not be detected by more bulk techniques such as NMR. And so that is one of the nice features, both the ability to see this dendrite, to locate it easily with the SXI, and then to choose identify the chemistry differences between those 2 regions. Now, in general, one thing that is somewhat challenging with XPS of these materials is assigning the proper chemical states to lithium. Lithium is a tricky one in that it has a low photoionization cross-section and does not produce, basically the signal strength is quite low compared to other components that are typically in these samples. It only has one peak position, the lithium 1s. There are no other photoelectron peaks, no Auger peaks, so you're essentially trying to characterize it based on one peak position. And the peak shifts are not very large relative to maybe some other materials as you go from metals to oxides. And it is quite reactive in itself. And so from this study, which I believe was done at NREL, they just looked at some of the values from the literature of different chemical states that people have reported, and they see that there's a wide range of what is reported. So when trying to define chemical states of your own sample, it's important to take a few precautions about how to set that up most effectively. And some suggestions are to make sure that your spectrometer is well calibrated. There is an ISO type procedure to calibrate your spectrometer based on gold and copper peaks to set the energy linearity and position. There was also a very nice set of practical XPS guides that just came out from the Journal of Vacuum Science and Technology earlier this year that are very useful for a variety of sample mounting analysis and setup kind of guides. Some other things you can do, rather than looking at just the absolute value of the peak position, you could look at the energy separation between, say, a lithium and an oxygen species. And what's really nice, if you had standards you could start with, then that can be very useful to essentially look at your standard materials, identify the relative peak heights, the relative separations between different materials of a given state, and then you can kind of use those constraints to help you identify the peaks in your own material. Some other things that we can do, looking at now toward more solid state batteries, we have used Auger analysis to characterize the interface between a LEIPS layer and a lithium cobalt oxide. And so with Auger, again, you have a peak for lithium that is at relatively low kinetic energy, as shown here. But we can actually identify slightly different positions of the lithium from the LEIPS and the lithium cobalt oxide. One thing, when you're working with these type of systems with an electron beam, you can cause damage to the sample pretty fast. And so what we have done here is use quite low sample current and relatively short measuring times to try to preserve the status of these materials. Another aspect of XPS is to use maybe a different photon energy, which will give you a different information depth. We talked about XPS with a soft X-ray gives you maybe 5 to 10 nanometers information depth. Using hard X-rays, such as chromium K alpha X-rays, can give you a deeper information depth, about 3 times that of aluminum. So this is an example of looking at a solid electrolyte material, a LLZO. And so LLZO is a candidate for solid electrolytes. One of the challenges is with the solid electrolyte and the solid anodes is that interface and making sure there is good contact and stable interfaces there. And so they're looking at a variety of different materials to provide wetting that can provide better wettability between the two. In this case, there was an LLZO pellets, and they are heat treating them and then applying an antimony surface coating to try to improve the performance of the material. But what we're looking at here is the kind of uncoated materials before or with a heat treatment. And so the top layer shows that the top figure shows that we are seeing a lot of lithium hydroxide type species, lithium carbonates a little bit on the surface. But if we look at this with HAXPES, we're looking a little bit deeper into it. We do see more of kind of an oxygen from the LLZO lattice, similar to the zirconium signal. We see a higher relative percentage of zirconium with the HAXPES compared to with XPS. So with that, we can understand that the lithium hydroxide type species tend to be more toward the surface, and we're looking a little bit below that with the HAXPES. So it's a non-destructive way of looking at different information depths and still seeing some different chemistries. Another technique we could use, this is an addition to the VersaProbe, is to do an electrical characterization using UPS and LEIPS. UPS is ultraviolet photoelectron spectroscopy. LEIPS is low energy inverse photoelectron spectroscopy. So just kind of as the name implies, I'll show on the next slide. With UPS, we are irradiating the sample with a UV source, about 20 eV, and then we are detecting photoelectrons. So very much similar to XPS. With LEIPS, we are actually irradiating the sample with electrons, and then it's producing photons that we can detect. And so what that allows us to do is actually get information about both the valence band side of things and the conduction band side of things. And so we can calculate things like the ionization potential with UPS and also the electron affinity with LEIPS. And so with these two different materials, the LEIPS and the lithium cobalt oxide, we can characterize the electronic properties of these two materials as well. Just to show in a little more detail what UPS and LEIPS, how they work together. Again, as I mentioned, UPS is similar to XPS in that we use a photon irradiation, generate photoelectrons from the valence states. With LEIPS, we are adding electrons with a given kinetic energy, and those will fill in the unoccupied conduction states and generate photons. And so you will end up with a figure something like this. And so we can look at the UPS data, determine the valence band max, which will help us understand the ionization potential. We can also, from the LEIPS, we'll get a photo signal where we can find the conduction band minimum, which allows us to identify the electron affinity from the vacuum level. And we can combine those together for the band gap. So in general, just want to kind of give an overview of the different options available on our different systems. With the VersaProbe, we have a variety of ion guns. That was something I did not really touch on, was the ability to sputter into your material to remove material to look at deeper layers. Of course, as you do that, you likely will change some of the chemistry, but we have some options and settings that you can use to try to minimize that as much as possible. We offer a C60 cluster beam, which is very useful for kind of inorganic and organic mixed materials, which tends to be what a lot of these battery materials are when you have the oxide, the electrode material, the electrolyte materials and whatnot. So that can be actually a pretty nice ion gun to use. We also have an argon gas cluster, which is very useful for fast sputtering of organic materials. And so what you may find is that your organic sputters much quicker, kind of leaving behind a skeleton of inorganic, which may be useful to you to understand that. We also can attach an Auger option to the VersaProbe, and that does give us some extra capabilities there. We have the UPS and LEIPS, which are on the system and in the same vacuum chamber. So we can do all of these different analyses within the same chamber. In addition, we have a variety of options for heating and cooling and biasing the sample in situ as well, which I'll touch on in just a minute. For our Quantes and Quantera system, the Quantes being our hard X-ray and soft X-ray system, we do have excellent base pressure, again, because these materials tend to be very reactive to atmospheric gases. It's good to have a good base pressure on the system to minimize those changes during your analysis. We can also heat and cool the samples in the vacuum chamber. And we do have the ability to transfer a sample from, say, the VersaProbe to a special auxiliary port on the Quantes or Quantera, and then analyze it using that system. We also have a special stage and holder where we can bias the sample in situ to perform polarization type studies. Similarly, with the 710, we have the sample heating capabilities, very good base pressure, transfer capabilities, as well as our electrochemical four contact stage for biasing. In addition to that, we do have some additional capabilities that are available on the Auger system for maybe some different types of analytical options. So we have EDS, which is going to give you more of a bulk elemental information than Auger. So those actually can work very nice together, complementary. And there's also backscatter electron, EBSD, so we can get more crystallographic information. We also have a FIB. So if you do want to do cross-sectioning and then look at interfaces, we can do that as well on the system. Again, lastly with the Nanotrough 3, very good base pressure, heating and cooling, the same transfer capabilities. And so you do have the ability to sort of work your way around the different analytical tools with the transfer capabilities, which is very nice for getting elemental versus high spatial resolution versus more organic or more long-range chemical molecular information as well. And a few of the different options for operando analysis. So we talked a little bit about using doing these studies outside of the vacuum system. So performing the voltage testing, the cycling testing, thermal testing, things like that, having to disassemble and then move it into the chamber. There are some options where you can do some of these types of studies in the chamber itself, sort of in real time. One option that we have is a special sample holder where you can actually sputter a anode type material onto your sample. And so you can monitor the evolution of species as you sputter that material onto the sample. We have a electrochemical cell where your sample would mount kind of in a cross section, and you can bias one side versus the next and look at any evolution of species across the cross section. And lastly, we have a special sample holder here showing that you can heat and cool. So we can go down to, I believe it's -140°C up to, in this case, 600°C, and there's another special sample holder that would go up to 800°C. So you have quite a wide range of temperatures that we can use for acquisitions. You can also use these terminals to attach leads to your sample, and then there are electrical feed-throughs that allow you to do electrical biasing in the chamber through the electrical feed-throughs. So there's some custom, and then we can always, we worked with several customers to customize special sample holders for maybe similar but not quite the same, and they want a little variation on their type of setup, but we'd be happy to work with you on those type of setups. And this is just a last example of how we can, of using an Operando XPS. In this case, we have a, I believe it's an electrolyte material, lithium foil up against it. And again, we're using the SXI, which is our secondary electron imaging, to determine exactly where the electrolyte material is versus the interface. And so we can see that and then drop points to analyze those two locations. Also using biasing in the biasing the sample at the same time. And so what you do actually see are that peaks do tend to shift as we bias the sample from 0.5 volt up to 2 volts, then back. So this is where it would be important to sort of decouple what you're seeing, charging effects of the kind of overall spectrum versus the chemical changes. And so some of the things we talked about, like looking at relative peak separations, ratios between different peak areas that might be different states, would all be very important for your characterization. And so just as an overview, we have between our Auger, XPS, and TOF-SIMS tools, we have a variety of options that would be very suitable for characterization of things like the passivation layers on our anodes, the SEI development, some of the dendrite formation, and some other questions that are being raised about optimizing these battery materials. We have complementary capabilities for high spatial resolution versus chemical information versus depth resolution between the different tools, with a variety of analytical options that we can add to them for electrical characterization, maybe different analysis depth without doing any kind of sputtering, heating and cooling, electrical biasing, cross-sectioning, and then the ability to transfer these between systems in a controlled environment is very handy. And so I think overall that kind of wraps up just a summary of some things that we can do with our systems for battery analysis.